Federated Adversarial Cross Training, FACT, is a novel approach to federated learning, FL, that addresses the distributional differences between clients. By leveraging domain differences between source clients, it identifies shifts in the target domain. In each Florida round, FACT cross-initializes a pair of source clients to generate domain-specialized representations, which are then used as adversaries to learn a domain invariant data representation. This approach has been demonstrated to outperform state-of-the-art models in both federated and non-federated settings on various benchmarks, including multi-source single-target and single-sources single-target experiments. The impact of communication restrictions and the number of participating clients on the performance of this method has also been explored. Federated Adversarial Cross Training, or FACT, is a novel approach for federated deep learning in the multi-source single-target setting, where non-independent and identically distributed, or non-i.i.d. data sources are present. This method capitalizes on interdomain differences between source clients and an unlabeled target domain, eliminating the need for concurrent access to both source and target data. By directly evaluating interdomain differences between source domains, FACT identifies domain-specific artifacts, enabling distributed training among clients. Empirical studies demonstrate that FACT significantly enhances target predictions on popular benchmarks, surpassing state-of-the-art federated and non-federated domain adaptation models. The approach benefits from the incorporation of additional source clients, remains stable with numerous small source clients, and can be efficiently applied under communication restrictions. The key advantage of FACT lies in its ability to leverage interdomain differences, facilitating the identification of domain-specific artifacts and enabling more effective distributed training. This leads to improved target predictions, even in the presence of non-i.i.d. data sources. The publicly available implementation of FACT makes it a viable solution for real-world applications, where data distribution and access can be a significant challenge. In the realm of machine learning and artificial intelligence, federated learning, FL, has emerged as a method to enable collaborative learning among multiple clients while preserving data confidentiality. This paper delves into the federated multi-source single-target setting, where data is both non-i.i.d. and distributed across numerous clients. Each client is associated with an individual domain, focusing on enhancing out-of-distribution performance on data from a single target client without training labels. The proposed approach attempts to exploit interdomain differences through adversarial learning strategies, aiming to learn a domain invariant data representation that increases the support of target samples. This is achieved by evaluating whether a sample is generated by the source or target distribution and suppressing domain-specific features. The paper also highlights various methodologies such as Federated Adversarial Domain Adaptation, FADA, and Federated Knowledge Alignment, FEDCA, which leverage local feature extractors to generate privacy-preserving representations that can be shared for distribution alignment. Moreover, the paper discusses source-free domain adaptation, which involves transferring knowledge from a pre-trained source model to the target domain and fine-tuning it exclusively on the target data. This approach ensures data confidentiality as only the pre-trained source model needs to be shared, requiring just a single round of federated communication. The paper concludes by emphasizing the significance of addressing the federated multi-source single-target setting, particularly in scenarios where data is both non-i.i.d. and distributed. Algorithm 1, Federated Adversarial Cross Training, FACT, is a novel approach to federated learning that leverages interdomain differences to maximize information transfer to an independent target domain without access to labeled data. The algorithm takes as input the round of federated learning, a global server model, a set of source clients, and a target client associated with private data. The server initializes two randomly sampled source clients with the global model and updates the local models using the cross-entropy loss function. The server then aggregates the feature extractors and broadcasts them back to the source clients. The source clients fine-tune their classification heads to fit the frozen feature extractors. The server shares the fine-tuned models with the target client and updates the feature generator to minimize the interdomain distance, IDD, by optimizing the IDD loss function. The IDD loss function measures the difference in classifications between two independently trained models on different source domains, providing a measure of covariate shifts. FACT consists of three main steps: source training, source fine-tuning, and target interdomain distance minimization, which are applied iteratively. The global feature generator is optimized to yield domain invariant representations for all domain-specific classification heads. The algorithm assumes non-i.i.d. data across clients and leverages the implicit interdomain differences to evaluate the support of an independent and in-labeled target domain. The IDD loss function is defined as the minimization of the expected difference in classifications between two models, encouraging agreement between target estimates. The FACT algorithm is a simple and highly efficient training scheme that enables the access to multiple source domains exhibiting individual characteristics, making it suitable for federated learning applications. Target client accuracy for 4 source clients on digit 5 data is presented in the table, highlighting the best performing methods within error bars. To mitigate domain differences, the classification heads and feature extractor are fine-tuned by minimizing the interdomain distance loss, updating the feature space. This approach enables the selection of the final model based on minimal interdomain distance, significantly speeding up training by reducing epochs and client communications. The full training procedure is outlined in Algorithm 1, which details the fine-tuning process. Notably, the fine-tuning step can be skipped for FACTNF, reducing communication costs but potentially affecting performance. This approach offers a trade-off between communication efficiency and model accuracy, allowing practitioners to adapt the methodology to their specific needs. By fine-tuning the feature extractor and classification heads, the method bridges the domain gap, ensuring more accurate client models. The interdomain distance loss serves as a critical metric for model selection, enabling faster training and reduced communication overhead. The presented approach offers a promising solution for federated learning scenarios, where domain differences can significantly impact model performance. The evaluation of FACT in various settings is presented, including multi-source single-target adaptation and standard single-sources single-target UDA. The results from Table 2 show the target client accuracy using 2 source clients on the Office dataset. The analysis includes different federated learning scenarios, such as negative transfer, varying the number of participating clients, and reducing communication rounds. FACT is also compared with state-of-the-art baselines, including federated and non-federated domain adaptation models. The implementation details are provided, utilizing PyTorch, with the code available on GitHub. The authors present the results of their proposed method, Federated Adversarial Calibration and Training, FACT, comparing it to various baseline models across multiple datasets. In a multi-source, single-target setting, FACT outperforms competing models with an average accuracy of 95.2% on the digit 5 dataset, particularly in scenarios involving SVHN and MNISTM as target domains. The fine-tuning step significantly improves model performance, especially for more challenging target domains. Similar results are observed in experiments using the Office and Office Caltech 10 datasets, where FACT outperforms baselines for 3 out of 4 possible targets, with notable enhancements after fine-tuning. Even in a standard UDA single-source, single-target scenario, FACT outperforms state-of-the-art baselines in 2 out of 3 scenarios for digit 5, demonstrating its capability to establish domain-robust models despite limited domain differences among source domains. The authors of this study delve into the performance of their proposed model, FACT, in various scenarios. They first discuss the robustness of FACT with respect to suboptimal source domains, highlighting that adding more source domains generally improves target accuracy for each target. However, they note that specific source-target combinations can already achieve high performance without additional sources, suggesting that minimizing interdomain discrepancy might prevent negative transfer. Next, the authors demonstrate that FACT can efficiently handle an increased number of source clients, maintaining its performance even when each source is split across multiple clients. This indicates the applicability of FACT in scenarios with numerous sources, each contributing small-sized data. Finally, the authors examine FACT's performance under communication restrictions, finding that frequent communication is not necessary for optimal performance. For the best-performing target domains, no significant change in accuracy was observed even with as few as 25 rounds of Florida. However, the more challenging target domains showed a decrease in performance with reduced communication, suggesting that frequent communication might be beneficial but not necessary in general. The research paper introduces a novel approach to multi-source, single-target domain adaptation in federated learning scenarios, leveraging interdomain distances for enhanced performance. This approach, named Federated Adaptation with Controlled Target Shift (FACT), combines two primary objectives: minimizing standard classification loss and interdomain distances. Experiments demonstrate that FACT outperforms state-of-the-art methods in most cases, including both standard UDA scenarios with a single source domain and federated scenarios where data privacy prohibits direct data exchange between clients. Findings also show that suboptimal selection of source clients has only a minor impact on target accuracy, and that FACT performs well when data is distributed across multiple source clients or under restricted server communication. However, the paper highlights the limitations of this approach, including the lack of theoretical guarantees for its applicability and effectiveness, particularly in non-i.i.d. settings where sample domain differences may be observed. It also notes potential restrictions on the use of large models in IoT devices due to resource requirements and increased training time, suggesting possible adjustments such as reducing communication rounds or neglecting fine-tuning. The study concludes that FACT is a simple, efficient, and competitive approach that could be valuable in many real-world federated learning scenarios. The research was supported by the German Federal Ministry of Education and Research (BMBF). Unsupervised multi-source domain adaptation is a crucial problem in machine learning and computer vision, where the goal is to adapt models to new, unseen domains without access to labeled target data. This challenge has been extensively explored in the literature, with key contributions including domain adaptation without source data, theory of learning from different domains, and practical secure aggregation for privacy-preserving machine learning. Approaches to unsupervised domain adaptation vary, including cluster alignment with a teacher, partial feature selection and alignment, and domain adversarial training of neural networks. Deep reconstruction classification networks, unsupervised multi-target domain adaptation, and information-theoretic approaches have also been explored. Furthermore, cryptonets, geodesic flow kernel, and multi-institutional collaborations have been applied to improve deep learning-based magnetic resonance image reconstruction using federated learning. The complexity and diversity of the problem are evident in the literature, with papers demonstrating the effects of non-identical data distribution on federated visual classification and the importance of residual learning for image recognition. A comprehensive approach to unsupervised multi-source domain adaptation is necessary to address these challenges. The thorough review of the literature sets the stage for the presentation of a novel methodology, which will be introduced subsequently. Federated optimization, domain adaptation, and transfer learning are crucial components in machine learning, with applications in on-device intelligence, medical image segmentation, and semantic segmentation. The literature review highlights key contributions, including federated optimization beyond the data center and on-device intelligence by Jakub Konechny et al. 1718. Domain adaptation methods without source data, such as those proposed by Vinod K. Kurmi et al. 19, and Rui Li et al. 20, are also discussed. The authors emphasize federated optimization in heterogeneous networks. 21. Multi-site fMRI analysis using privacy-preserving federated learning and domain adaptation. 22. And source hypothesis transfer for unsupervised domain adaptation. 23. Moreover, they cite research on feature disentanglement for multi-domain image translation. 24. Federated domain generalization on medical image segmentation. 25. And secure federated transfer learning frameworks. 26. The review also covers source-free domain adaptation for semantic segmentation. 27. Conditional adversarial domain adaptation. 28. And communication-efficient learning of deep networks from decentralized data. 29. Secure machine learning systems, such as Secure ML, 30, and high-performance deep learning libraries like PyTorch, 31, are mentioned. Furthermore, moment matching for multi-source domain adaptation, 32, is discussed. This comprehensive review underscores the significance of federated learning, domain adaptation, and transfer learning in various applications, highlighting the need for continued research in these areas. This section of the research paper provides a comprehensive overview of various studies and methodologies in the field of domain adaptation, with a particular focus on federated learning and multi-source domain adaptation. It begins by discussing the concept of federated adversarial domain adaptation, which aims to leverage the benefits of both adversarial training and federated learning to enhance domain invariance across different data sources. The paper then delves into the concept of multi-source unsupervised domain adaptation via pseudo-target domain, where the authors propose a novel approach to adapt visual category models to new domains using a pseudo-target domain. This is followed by a discussion on adapting visual category models to new domains through the use of a domain adaptation network. The authors also explore the concept of maximum classifier discrepancy for unsupervised domain adaptation, which involves training two classifiers to maximize their discrepancy on the target domain, leading to better adaptation performance. In addition, they discuss the idea of style-driven source-free domain adaptation in clustered federated learning, which proposes a novel approach for domain adaptation in a clustered federated learning setting. Furthermore, the paper touches upon the topic of federated multitask learning, which demonstrates how federated learning can be applied to multitask learning scenarios. It also highlights the importance of deep correlation alignment for deep domain adaptation, a method that aligns the second-order statistics of source and target domains to achieve better adaptation. Moreover, the authors examine feature distribution matching for federated domain generalization, a technique that aims to align the feature distributions across different domains in a federated learning setting. They also discuss deep domain confusion, maximizing for domain invariance, which introduces a novel approach to enhance domain invariance by maximizing the confusion between source and target domains. The paper also reviews the concept of adversarial discriminative domain adaptation, which leverages adversarial training to improve domain adaptation performance. Additionally, it discusses knowledge aggregation for multi-source domain adaptation, a method that aggregates knowledge from multiple sources to improve adaptation performance. The authors also explore the issue of negative transfer in domain adaptation, emphasizing the importance of characterizing and avoiding negative transfer. They also discuss adaptive adversarial network for source-free domain adaptation, a novel approach that adapts the adversarial network to the target domain without requiring labeled target data. Moreover, the paper delves into the topic of federated multi-target domain adaptation, which proposes a novel framework for adapting models to multiple target domains simultaneously. It also highlights the importance of gradient matching federated domain adaptation for brain image classification, a technique that aligns the gradients of the source and target domains to achieve better adaptation. Finally, the authors discuss the concept of federated learning with domain generalization, which aims to enhance the generalization capabilities of models across different domains. They also review multiple source domain adaptation with adversarial training of neural networks, a method that leverages multiple source domains and adversarial training to improve adaptation performance. The authors draw connections to existing works in the field of domain adaptation and federated learning, referencing Sicheng Zhao et al.'s 2020 multi-source distilling domain adaptation approach and Yu Zhao et al.'s 2018 work on federated learning with non-i.i.d. data. They also mention Jun Yan Zhu et al.'s 2017 cycle-consistent adversarial networks for unpaired image-to-image translation, highlighting the use of adversarial losses to align distributions between domains. This work is pertinent to the current study's proposed approach, which involves adapting models to new domains and tackling the issue of non-i.i.d. data in federated learning. The implementation details of the Digit 5, Office, and Office Caltech 10 datasets are outlined. For Digit 5, the feature generator consists of 2 convolutional layers, and the classifier consists of 3 fully connected layers, as detailed in Table 5. The architecture includes batch normalization layers and ReLU activation functions. Specifically, the feature generator employs 2 convolutional layers with batch normalization, ReLU activation, and max pool, while the classifier includes 3 fully connected layers with dropout, batch normalization, ReLU activation, and softmax. In contrast, for Office and Office Caltech 10, a pre-trained ResNet 101 provides the generator, and the classifier consists of two fully connected layers. The model architecture is specified in Table 5, which shows the layer configuration for the feature generator and classifier used for Digit 5, as well as the classifier used with the pre-trained ResNet 101 for Office and Office Caltech 10. For the single source's INGL target unsupervised domain adaptation setting, the target accuracies obtained by FACT for all possible source target combinations on the Digit 5 data are presented in Table 8. These results are averaged over 5 repeated runs. Notably, to run FACT without modifications, the source data is equally split between two source clients, which may decrease target convergence due to sample-dependent distributional differences between the two sources. Therefore, a higher initial learning rate of eta 0 equals 0.01 is used for these experiments. The number of samples for each dataset and domain is provided in Table 6. Specifically, for Digit 5, the total number of training samples is 107,348, and the total number of testing samples is 37,860. For Office, the total number of samples is 4,110, and for Office Caltech 10, the total number of samples is 2,533. The training and testing splits for each dataset are also specified. In Table 7, the number of classes for each dataset is presented, with Digit 5 and Office Caltech 10 datasets having 10 classes, while the Office dataset has 31 classes. Table 8 outlines the target accuracies obtained for the standard single sources INGL target unsupervised domain adaptation (UDA) setting across all possible source target combinations of the Digit 5 data. When using MNISTM as the source and MNIST as the target, an accuracy of 99.17 plus or minus 0.04 is achieved, indicating a high level of adaptation between these two datasets. However, when MNIST is used as the source and MNISTM as the target, the accuracy drops to 61.27 plus or minus 2.85, highlighting the challenges of domain adaptation and the importance of effective UDA techniques. When SVHN is used as the source and SIN as the target, an accuracy of 95.74 plus or minus 0.13 is achieved, demonstrating a high level of adaptation between these two datasets. However, when USPS is used as the source and SVHN as the target, the accuracy drops significantly to 12.19 plus or minus 1.97, indicating a more challenging adaptation scenario. These findings underscore the variability in domain adaptation performance across different dataset combinations, emphasizing the need for robust and adaptable UDA algorithms. The research also suggests that understanding the characteristics of each dataset and their interactions is crucial for achieving optimal adaptation results.